Okay, in this video, we are going to go over linear and quadratic regression. And so to get us started on that, we're going to explore the linear and quadratic patterns so you can see how that works on a data set. So on this first one here, they gave us the term numbers and the term, and it's asking us for the differences. It says these terms are called the first differences. So since these are all an equal distance away, I just need to look at the y values differences. And so this would be a +2 to get from 1 to 3. And then again, a +2, +2, +2 as we go from 3 to 5, 5 to 7, 7 to 9, and 9 to 11. And so in these first differences, these are all the same. So this pattern is considered linear. It is linear when it has a constant difference for our y values there. Since they are the same, this would be linear as the pattern. All right, for our second one here, it says fill in the pattern representing the number added to each term to get to the next term. So again, we're looking for those first differences, and we can do that because these are an equal distance, our x values or our independent variable. And so from 1 to 2, we've got a difference of 1. From 2 to 5, we have a difference of 3. And then 5, 7, and 9. In this case, these first differences are not the same. So this pattern would not be linear. And so we take that same table and we're going to look at the second differences. So our first differences were our differences of the dependent variable here. So we're going to take those differences and find the difference between them. So we're going to find the difference between 1 and 3, which is 2. 3 and 5, that's also 2, 2, and 2. So in this case, our second differences are the same. And so when our second differences are the same, it is considered a quadratic or second degree polynomial. This would be true as well if the second differences were not the same and it went to the third differences, then it would be considered cubic or a third degree polynomial. So identifying our differences here allows us to determine what type of pattern and equation we want to use. So here's a couple examples. If you'll go ahead and pause the video, see if you can figure out what the differences are and if it is linear or quadratic. So now we can see our differences on this first example here. Our first differences are all 3. It's got a constant first difference there. And so this pattern is considered linear because the first differences are the same. On our second pattern here, the first differences were not the same, so I know it's not linear. My second differences are the same, so this is quadratic. And then for my last one, same thing. First differences were not the same. The second differences are the same. So this is quadratic. Our second differences are the same. Now we were able to do that because we gave you perfect functions there. They had the exact same differences. Sometimes in real life data, you're not going to get the exact same first difference the same, or second difference, or third difference the same. So we're going to look at those regressions next. So on our next page here, sorry about that. Here we go. We have some information on linear and quadratic regressions. So here is a real life situation. In this case, we need to analyze the data a little bit differently because if we look at our first and second differences, we're not going to get an exact value. Right here, you see this difference is 5, this one's 4, this one's 2. So we're not going to be able to look at it just from the first or second differences. We're going to have to use something else. It tells us a convenience store manager notices that sales of soft drinks are higher on hotter days. So he assembles the data in the table. So we've got our independent variable is the temperature, and then our dependent one is the number of cans sold. So we're going to learn how to look at this on the calculator first. And so here is my calculator. I'm going to hit stat, which is this one right here, and then edit. And we're going to put in our data that we have there. So you're going to put in all of your independent into the L1. And then all of our dependent variables into the L2. All right, so I have all of the information in there. You do want to make sure you double check those numbers, verify that they're exactly the same as the table, because even one digit off is going to throw your whole equation off. So make sure that you double check that. All right, so now we're ready to look at the scatter plot that we've just created. That's what we did when we put it into stat. So if you hit second y equals, that takes you to your stat plot menu there, and you want to turn it on. So there is our stat plot. We've turned it on. You can also do that by going to the y equals and making sure you highlight that top part. So move up to the top, highlight it, and that turns it on. So to see our scatter plot here, I am going to make sure that the window is open to see these values. So for our x min, we have -10, and our x max, we have +10. That's not going to show any of these values. I need to open that up. So I'm going to go ahead and change that to 0, and I'm going to go somewhere above this 84 so I can see all of these values. So I'll go to like 90. For the y min and y max, I need to see these dependent variables here. And so our smallest number is 320, our biggest is 780. So I want to make sure I open the window up big enough to see that. So I'll go to like 250 and 800. That will allow me to see all the points. Now when I hit graph, there is our scatter plot. You're always going to want to look at that scatter plot to determine, does it look like a line? Does it look like a quadratic? Which one is going to be the best one for this? Now, to help us with that, we do have some diagnostic tools that will do it. So if you go to mode, and then come down to where it says stat diagnostics, and that's usually off, and you can turn it on by highlighting and hitting enter. And so that's going to go ahead and turn that on for you. And now we're going to have the calculator calculate the equations to check. So it tells us to make a scatter plot of the data in the calculator, and then it wants us to find and graph a linear regression equation that models the data. And we're going to round each coefficient to 3 decimals. So we're going to hit stat, and we want to calculate this time. So we're going to highlight the calc part. We're going to move that to the right, and we want a linear regression. So that's that one right there, number 4. And so it says the X list is L1, and that's true. That's where we put our independent variables. So I'm just going to move right along. And Y list is L2, and that's correct because we put the dependent there. Now, where it says store regression equation, the calculator is asking you, what do you want me to do with this equation when I've written it? And so if you hit alpha trace, you can plug it into the Y1 or the Y2 or anything. It helps you use the equation after you have written it. And so now we hit calculate, and the calculator gives me the equation. So let's write that equation down. We said 3 decimals, and so we're going to do 16.137x because it tells us that that's the a value right there. This is my a value, so that's what goes in front of the x, and then this is my b value, so that's my y-intercept. And so I'm going to get negative 573.375. Now, the next thing it asked me here is the R2. That is our correlation coefficient. And so when we turned the stat diagnostics on, it gave us that R2 value right there. So 0.999. Oh, sorry, we wanted 4 decimals, so 8.9986. All right, what that correlation coefficient tells us is how close is this equation to our data. And so there's a couple things you want to look at it. The closer it is to 1, the stronger the correlation. And then the closer it is to 0, the less correlation there is. This is really close to 1. So that tells us that is a great equation that you're using right there. So it tells us to use the model to predict soft drink sales if the temperature is 97. Since I stored my equation in Y1, if I hit graph, first off, it's going to graph the equation, which allows you to see that that's a good equation as well. We're going through most of these data points. But since it's in Y1, I can hit second window, and I can just take my table 297, which is what we're looking for. And so when I hit second graph to go to our table, there it is at 991.88. Now, since these are soft drinks, I would want to keep it as a whole number. So I would say 992. So let's recap on that because we just did a lot of things there. We turned on our stat diagnostic so we could get our R-squared value. That's the only way you're going to get an R-squared value. We turned our stat plot on right at y equals. It's that value, it's that highlighted part right there that tells you that it's on. Then we hit stat to put in our information. We did the edit, and to calculate, we did the calculate part on the right. All right, we're going to try another one here. It gives us the table shown. The table shows the population of a city every 10 years since 1970. And so there is our table. Make a scatter plot in the data in the calculator and find the graph of a quadratic regression. So this time we're going to try a quadratic regression for it. The process is exactly the same. So go to your stat. Here it is, stat, edit. And we're going to put in the new data. Now you can go to your L1 there when it's highlighted and you can hit clear. Do not hit delete because then that's going to delete the entire column. So you do not want to use that one right there, delete. You're going to hit clear and then enter and that will clear the column for you. And so we get 0, 10, 20, 30, 40. Whoops, that would mess me up. All right, so we put that in and we verified those are the same numbers that are in the table. Remember, even one digit is going to throw your values off. Now we go to stat and we want to calculate and we want to do the quadratic regression this time. And so I'm going to hit L1, L2. At store regression equation, we hit alpha trace. That's going to get me my menus for my y values. And so I'm going to put it in the y1, and then I'm going to hit calculate, and there is my equation. So this, since it's a quadratic, it's going to be the ax squared plus bx plus c. And so there's my a, my b, and my c. So I'm going to go ahead and write those down. We want to keep 3 decimals. So there's our equation rounded to the 3 decimal places and then our R squared right here. Again, we're really close to 1, so that does tell us that the equation is good. Now the calculator is just doing its best to match that data. So you always want to check and really think through the problem as well to figure that out. Then it tells us to use the model to predict the population in 2030. Remember, this is the number of years since 1970. So from 1970 to 2030, we're talking about 60 years. And so we're going to want to put in 60 in the calculator to do that. Since we stored it into our y equals, easy peasy, we just hit second window, and I want to go to 60 years and then go to my table, and there it is at 5637.6. And that is in thousands. Our table told us that. Okay. If you wanted to actually write it in thousands, we could also write 5,637 million. Oops, one too many zeros there. There we go. So we can multiply it times the thousands in order to get the population number value itself. All right. On the last two scenarios, they told us to write a linear regression or write a quadratic equation. If the problem tells you what it is, then that's obviously the one you're going to want to do. So if it says linear regression, do a linear regression. If it says quadratic, do a quadratic. In this case, though, they're not telling us which one it is. And so it says anthropologists use a model that relates femur length to height. The model allows an anthropologist to determine the height of an individual when only a partial skeleton, including the femur, is found. Analyze the data in the table by finding a linear and a quadratic regression. So in this case, they're relating femur length to height. So you want to think about that scenario. Does that scenario sound like a linear scenario or a quadratic one? So always keep that in your mind. Then create a scatter plot so that you can see the data. So we're going to go ahead and put that into our table. So again, I'm going to go to Stat, Edit. I'm going to clear, not delete, my list. And then I'm going to put in my independent and dependent. So let's go ahead and get that done. All right, so there is my stat plot. It is in, so now we want to see it. I'm probably going to have to adjust my window again because remember we had adjusted it for the other one, so we want to make sure we see this data really well. So 0 could still be my minimum. I need to see all the way up to 50, so I want something above that. I'm going to go to 70 should be enough. On this side here, my smallest value is 155. My biggest value is 179, so I want to see at least to that. So I'm going to go 0 to 200 there. That'll allow me to see all those values. So I hit graph, and actually that's not a very good picture. So let's look at that window again. I went too far, I think, with the 0 to 200. So I'm going to go from 100 to 200. Let's see if that gives us a little bit of better picture. Still not great, so I'm going to keep going. Let's try 120 to 190. There we go. That's as good as I think it's going to get. Actually, let me try a little bit of a, there we go. All right, so now that we have our points there, in this case, we want to go ahead and write the equation in both linear and quadratic so we can start thinking which one is the correct one since it's not going to tell us which one. So I hit Stat, Calc, and I'm going to go to linear regression. And I'm going to put this one into Y1, and then I'm going to hit calculate. And so here is our equation. So let's get that written. Y equals 1.923x plus 80.681. And our R2, our correlation coefficient, is 0.9328. That is pretty close to 1, so that may be a good equation, but we're going to go ahead and try the quadratic as well. So I'm going to hit Stat, Calc, and this time I'm going to go to quadratic regression so that the calculator writes a quadratic equation. The calculator is going to write whatever equation you tell it to. So with the linear regression, quadratic regression, cubic, quartic, natural log, it is going to write whatever equation you tell it to write. Whether it's good or bad, it's still going to be the one it writes. So the store regression equation, in this case, I'm going to hit alpha trace Y2. Can't see that. And then I'm going to hit calculate. So now we've put the linear equation into Y1 and the quadratic into Y2, so we can look at it that way too. All right, let's go ahead and write our equation again. We're going to write that with 3 decimals. So I get Y equals 0.042 x squared minus 1.757x plus 160.910. When it says 3 decimals, we do have to have 3 decimals, which means that that 0 does have to be there at the end. If you leave that 0 out, it could say that's as far as it goes, but this number goes way further. So when you're rounding, make sure that you round it correctly. That turns into 0.910. All right, so for our R2, our correlation coefficient, we've got 0.9396. Well, that's pretty close to one as well. These are very close to one. So this is saying really either one of those could work. Um, Quadratic is technically closer. So we could say that the calculator is saying that's a good one to write. Let's look at the graph to see what we think. So if we hit graph, there is my linear equation, and there is my quadratic equation. Now, if I'm looking at just this data, I would say the linear represents it better because as we move through here, that is right in the center of those points where it looks more like a straight line growing. On our quadratic, which is this red one, it is curvy. And so it's kind of not in the middle of these points right here. And it's kind of leaning towards these points. And then it goes up over here as well instead of going through the middle. So in looking at the graph, I would say linear is a better data set for this one. So as we look at it, the shape is definitely better on the linear because the data points look straighter. All right, so based on our observation and knowledge, which regression is a better fit for the situation? So this is where you really have to use all the knowledge you can. The calculator is going to give you whatever equation you tell it to write. But let's think through this. So it's talking about the femur length compared to the height of somebody. Well, that's not going to really be represented by a quadratic graph because that's a curve. And so if we think about your femur length, it's going to be the longer it is, the taller you are, the shorter it is, the shorter you are, and it's going to grow at a constant rate. As that femur grows, you're going to grow in height that way. So that represents more of linear data just by the context of the problem. Yes, the correlation coefficient looked closer on the quadratic, but it wasn't very significant here. Both of those are very close to one. And then when we looked at the graph of this, it too looks straighter as linear. So we should say that the linear regression is the better of the two, using all of our knowledge. All right, so we could say the data aligned better with the line. And then we can say the context of the problem is better represented by a line. So the calculator is a tool, but you're the one that really needs to analyze the situation. All right, so it says an anthropologist finds a femur of a length of 58 centimeters using the better model predict the height of the person. All right, so we said that the line was the better one, so that's our Y1. So when I hit second table and I go to 58, I'm going to want to look at the Y1. As you can tell, they are not far apart, but there is a difference between them. And we said the linear was a better model, so that's the one that we would want to keep. So 192.22, and this is measured in centimeters, so we'll go ahead and put our correct unit. All right, for the ending part here, I will let you know that as you're using your reasoning skills to help you decide which regression to use. While R2 can be very helpful, it should not be the only information used to determine the regression. When the R squared value is approximately the same for linear and quadratic models, check the shape of the scatter plot to guide you in choosing the appropriate model for the situation. Also think through the context of the problem. Would it represent something that's parabolic or something that's linear? And then the last part, a helpful hint, if a quadratic quadratic regression has an A value close to 0, then the linear model is probably better. All right, so let's think about what that means. Right here, this was close to 0, which means that 0 times x squared would be 0, which takes this away and makes it linear. That's why we say just really look at the problem, think through all of that portion of it. If this a value is close to 0, then you're probably looking at a linear equation, not a quadratic one. All right, there's your regression information.